Hi everyone, my name is Nachiket, Kale, and I should be presenting on separated flow control and diffusers using pneumatic and plasma-based actuators. This work is done, it's funded by Rolls-Royce, and I'm from the Aerospace Engineering Department. So although I'm working in flow control per se, eventually you'll realize that it's not classic control, it's got lots of elements of core aerospace engineering, propulsion basically. So that's the outline. I'll start with describing what jet engine diffusers basically are. Then I'll move on and describe what flow separation means. I'll go over to how you do flow control on a given flow field. Then I'll start with the actuator devices that are required for the flow control. Then we'll move on to the diagnostics that people typically use to study any kind of gas dynamics or flow fields. And I'll discuss the results briefly, and we'll go to the conclusion. So that's a jet engine. It's probably one of the more complicated designs in engineering. Very simplistically, you have an air inlet which takes the air in. You have the compressor stage, a multi-stage compressor which compresses the air into a high pressure gas. Then you go into the combustion chamber where combustion happens, and eventually you have the turbine, which essentially is connected to the shaft that runs the compressor. So the compressor derives its power from the turbine. The gas spins the turbines and it's ejected through an exhaust through a nozzle to shape the flow of the gas. We'll focus on the inlet diffuser part of things. So right before the air enters the inlet, you have a device which is known as a diffuser. Generally you need a Mach number, which is the ratio of the speed of air to the speed of sound at that particular temperature. You need that ratio at the compressor stage to be around 0.45 to 0.55, about half the speed of sound, so that your compressor performs the optimum. But the aircraft flies at a different speed. Usually things like Boeings or Airbuses, they do fly at approximately 0.85, 0.87 Mach. So what you need is you need to take the air in and you need to slow it down so that you have the speed around 0.45 Mach at the compressor stage. And that particular thing in subsonic, high subsonic and supersonic engines is done by an inlet diffuser. It takes the air in, it slows it down. And if you remember the Bernoulli principle, it's not completely applicable to this Mach number, but if you have an expanding area, you have reduction in velocity and you have an increase in pressure. So the gas undergoes a decrease in velocity and subsequent increase in pressure. I'll describe flow separation and then how it applies to diffusers in particular. So in general, there is a concept known as a boundary layer in flow. So if you consider viscosity, if you consider a flow moving around the body, extremely close to the body, the interaction of the fluid with the solid surface is extremely viscous, and that creates a tiny layer. It's usually of the order of a couple of millimeters in normal aircrafts, couple of millimeters to a few inches or so. And that in that particular layer, the viscous effects substantially dominate the inertial effects. It's the boundary layer that is the source of the flow separation. So if there is a boundary layer flow, and if that flow is facing an adverse pressure gradient, if it has to move from a field which is low pressure to high pressure, at one point of time it fails to stay attached to the surface of the body and it separates. So you can look at the image on the right, top right, that's flow separation over an airfoil. You can see on the top surface the flow is given by the oil flow ways of the streamlines, as you can see. The flow is attached right up to the tip. The bottom surface is completely attached, but on the top surface the flow fails to, I should use this. The top surface of flow fails to stay attached and it kind of just gets separated. And then you have this whole area of recirculation where you have reverse velocities and separation bubbles. This also happens in a diffuser. So a diffuser basically is a wall that moves away, as I described it. It moves away to, out here. It comes in straight and then moves away for the flow to decelerate. You have flow separation at a particular point in the diffuser, and then you again get a similar reattachment, a separation bubble, a recirculation zone. The adverse effects of having flow separation in general are, it leads to lift reduction in wings, in aircraft wings, and a sudden stall. So as long as the flow is connected, it's attached, it's not separated, the aircraft flies smoothly. Suddenly you have the flow separation, you have an extreme loss in lift, and you have that effect of the aircraft going down, which is what stall essentially is. You have an increase in drag. In compressors and turbines, you have stalling of the blade. A blade essentially is a wing, except it's placed in a different orientation. In diffusers, you have a reduced pressure recovery. So pressure recovery basically is the ratio of the total pressure at the compressor stage to the inlet stage. So it's the amount of pressure that you have recovered from the complete flow. The amount of pressure energy you have recovered from the kinetic velocity energy is defined by the pressure recovery. That goes down, and you have increased distortion and turbulence at the fan phase, at the compressor stage. So then we go into flow control. So flow control essentially is defined as manipulating the flow so that you obtain the desired flow field. In our case, we want to manipulate the flow so that it stays attached to the body and doesn't do the whole detachment thing. There are certain ways of, not extremely comprehensive, but the rough ways of categorizing flow control into 4 sections. Like, you can either use tangential blowing. You can use a jet to blow tangential to the surface where you want the flow to stay attached. A jet which is artificially created, not the core flow. You can use suction. You can use some devices that suck some air suck some momentum out of that particular region. You can use vortex generators, which are devices that create vorticity in the flow. Vorticity is it's defined as well, essentially, if you have any flow that doesn't have a single directionality, then you usually have vorticity. Forced excitation is where you would impose a certain frequency of oscillation or a perturbation or disturbance into the core flow and hope that it affects it the way you want. And roughly the 2 ways in which these 4 things work. The first to work by energizing the boundary layer, the low momentum region, which is extremely close to the wall. And the other 2 generally work as they enhance the convective transport of free stream momentum, which is there already is a certain vertical structure that exists in any flow very close to the surface. These usually end up either enhancing or manipulating those vertical structures to increase the momentum, and so sort of it helps to entrain the velocity to stay closer to the body and not get detached. It'll be probably more clear in the next slide. There are 3 ways basically of dividing the actual devices that you use to control the flow, and they are the passive and the active, and then the hybrid control. So in the passive control, you have something known as an always deployed uncontrollable device, which essentially is always there, like vortex generators, vanes, microrams. On the top right, you can see the structure of a split microvane, where you have 2 incoming tiny structures placed on the surface, and then you see vorticity being created that leads to flow control. You have spoilers like you see on aircrafts or even F1 racing cars. You have active control like synthetic jets. Top right you see, bottom right you see a synthetic jet, which essentially is a cavity and an oscillating diaphragm. It leads to a periodic ejection of gas out of the tip of, out of the mouth of the cavity, which again turns out to be counter-rotating vortices. And if you place this at the wall, on the flush to the surface of the wall, you can control the flow. You have continuous jets, which is just blowing a jet out. You have plasma-based flow control, which I'll eventually decide as that's the actuators that I've used for my research. And then you have a hybrid, which is a combination of 2 of these active and passive devices. So let's go to the flow control devices that we have chosen. The first one is a pneumatically enhanced and or deployed actuator. It will refer to it as PIDA. You can see on the right, you can see on the top right figure out here, these tiny devices, 1, 2, 3, 4, these are the actual actuators. So the right out here is the upstream end of the body from where the flow comes in. The left is the downstream end. And from the slit in that particular, this slit out here, you have a pneumatic jet that continuously blows out tangential to the wall. And then this particular triangular structure out here is a micro ramp, which creates the vorticity that you require to again have flow control. On the bottom, this is a standard body called the Glauert-Goldschmidt model, which is a benchmark to study flow separation. Out here, the left is the upstream and the right is the downstream. The flow comes in from the left, it travels this whole curve very nicely, and then it suddenly finds this adverse pressure gradient, the wall moving away from the body, and it separates at a point somewhere around here. So this row out here is the actuator devices, where the jet would blow from this slit onto the right, so in the direction of the flow. It's a combination, it's a hybrid controller where you have vortex generator, that triangle piece, and a steady jet. And it leads to a Coanda-like effect where the flow tends to stay attached to the body even if the body is moving away from its direction. It also energizes the boundary layer. The exact reasons for the effects are still being explored. The second flow control device that we have chosen to use is known as the localized arc filament plasma actuators, LAFPAs in short. What we do out here is we create electric arc plasmas between two electrodes that are embedded in a cavity. And so if you look at the bottom flow chart, you'll see if you feed power to the device, it will create plasma. It will create a breakdown of air between the two electrodes. Then you'll have excitation of the rotational vibration electronic modes. You'll have the radiation, which you see as the bright spark light. It's basically lightning, creating lightning in a small form. Then the translational modes are excited, and then you have increase in the temperature and pressure of that area, and eventually that leads to a tiny blast wave. It's like tiny detonations at high frequency. It's an active control because you obviously can control the frequency of your jet formation, of your arc formation. I'll just briefly describe the difference. So that's a wind tunnel, a high supersonic wind tunnel. You see some devices that lasers and cameras and stuff like that, and you see the body embedded out here. So that's where we study the PDAs, the pneumatically activated devices. And that out here is the experimental setup for the LAFPAs, the plasma-based ones, where you see the circuit, which is not, it's just there for the sake of completion. This stuff involves high voltage. It uses about 10,000 volts to break down the air between the electrodes, which is why you have everything scaled up. All the resistors are huge and all the lines are extremely low gauge. Then we'll move on to the standard diagnostics that are used by people to study gas dynamics. Emission photography, as it suggests, it's basically just taking photographic images with high resolution, high speed cameras of the light emitted, be it in the visible range or in the non-visible range. Schlieren imaging is an interesting technique. I won't go into the details of that, but what it gives you at the end of it, at the output, is basically the second gradient of the density field. So if you have a density field, like just to give you an example, a mirage that you see on hot days is essentially a density gradient you have between the hot surface, hot air on the bottom and the cold air on top. So an image you see through the mirage is basically a first gradient of the density that you see as a shimmering. Schlieren is the second density. It gives you some more information about the density fields. I'll go into some images later on that might be more clearer. PIV, particle image velocimetry, what you do is you seed the flow with tiny particles, something known as tracer particles, what you can call as tracer particles. You take 2 snapshots of that flow at very quick, rapid successive timings. The time difference between the 2 snapshots, say it's delta t. If you trace the particle where it was in the first image and then where it is in the second image, you get the distance that it has traveled, that's delta s. Delta s by delta t gives you the velocity. That's how you can obtain the velocity field of the whole area just by using seeding and double images. Spectroscopy is where you take in light and then you perform the spectral analysis of what frequencies of light you see and at what intensities you see them. Electrical characterization, basically the voltage and current and stuff like that. Static pressure measurements, you have pressure tabs that measure the static pressure of the flow along the walls and along the bodies. You have surface flow visualization, which essentially is you paint or coat your structure with a mixture of oil and some fluorescent or some visual dye. And when you turn on the flow, you have the streamlines that you could see on the image of the airfoil. You can see the streamlines as the oil illuminated. Pressure sensitive paint is again a way of measuring the pressure on a surface. It's basically sensitive to the pressure, the intensity of the light that is displayed by the surface of the paint is proportional to the pressure that it sees. I'll explain helium tufting when we come to that. So I won't go into all the details of all the diagnostics that we have used because they'll just make it too large. Just show some snippets. So on the top left, you can see 2 electrodes coming in and you can see an arc formation out here. This is Schlieren imaging. And then you can see the blast wave created that's propagating slowly. So this is phase locked averaged images over multiple time samples, which have been then collected together to give you some sort of a movie. On the bottom, you can see the location of the blast wave as it moves along. On the right, it's an interesting application that we did. We used iridium coated spark plugs that are the best spark plugs available for automotive purposes today. And we created arcs between them. They're substantially weaker because the gap separation out here is lower, but you can faintly see the blast wave moving out from the both ends. We have held one blast wave constant, we have manipulated the other blast wave so that it moves out. The second is of the LAFPA, the plasma-based actuator. The first one was just an arc formation. This is an actuator. So what you can see out here is a piece in which a cavity is bored. So if you can imagine there, this would look like the cross section of the cavity. And you can see the two electrodes coming in from the bottom. They are not flush with the top surface, they are recessed into the cavity. So you create a controlled environment for the cavity, for the plasma, where you can shape the gas that's being ejected. If you look at the right image, the cavity is oriented at a 45-degree angle, and so you can see the hot gas that's ejected. It's ejected at a 45-degree angle. So it almost looks like a cannon ejecting hot gas, and that's basically what we need. We need a directional, controlled ejection of gas. And then you also have this added bonus of a blast wave, which may or may not affect the flow. It's yet to be determined. The second model is it's of the particle image velocimetry based on the PIDA, on the pneumatic actuators. For some strange reason, I don't see two images out here. I'm going to miss them. So what I'm trying to show is, on the left, this particular geometry that you see is the downstream end of the actuators. I'm sorry, it's the downstream end of the body that faces separation. So if you remember the previous Glaude cold body that we had, it essentially had a rising curve where the flow stays attached, and then it suddenly dips down where you have the separation. On the left is this. Here you can see a substantially huge separation bubble. It's with a low jet actuation. On the right, you see an actuated image, and the separation bubble has decreased in size. This would have been more, the contrast would have been more apparent had I not forgotten to put or see the two images out here. The first image on the left was of uncontrolled, without any actuation, so you could really see a huge separation bubble. I might come to it at the end if I have time, if I find that image. The next one is the pressure sensitive paint done on the pneumatic actuators. This paint, you can see it's colored differently. It's basically an enhanced visual effect using ultraviolet lights, color mapped onto a visible light color, and different intensities tell you different pressures. What we have used it in a unique way. What we did was, we have these holes that you see out here, those are static tabs. Those are tabs built into the base of the wind tunnel, from which you can measure the static pressure at that particular location. Now that static tab we have used in reverse direction. We have fed very thin, tiny jets of helium that jet out of those tabs, and they essentially create something like fake tufts. Like if you imagine what you're trying to do, imagine a flow. Imagine a flow in a wind tunnel. Imagine pasting thin threads, like tiny segments of threads, in a nice grid fashion all over the base of the wind tunnel. If the flow changes direction, the tufts will change direction. It's like wind flowing in a field of grass. The grass bends according to the direction of the flow. We are using the same effect by doing a virtual tufting with the tiny jets of helium. So these tiny jets of helium interfere with the pressure sensitive paint, and they tell you the direction in which the flow is going. So you can see on the left, there is no actuation of the actuator. This part is the downstream end of the model. This completely lies within the recirculation zone, within the separation bubble, and the flow is going from top to bottom. So as you can see on these particular static tabs, the helium jet is pointing upwards. So you can see that the flow has already reversed in direction. It's going from the downstream end to upstream end, which is the classic definition or a classic symptom of a recirculation zone, the flow going in the reverse direction. After turning the actuators on, the pneumatic actuators on, you can see the helium tufts, they have started all blowing in the downstream direction, downwards, which means that the flow has managed to attach somewhere above this line, upstream of this line, and now it is flowing smoothly as it should, hugging the surface of the curve downstream. Should play a movie. I guess I'll just play that. Let's see if I have enough time to do that. Do I? I have 1 minute of a movie.
Okay.
That's my last slide.
Sure.
So what you see out here is a movie that will show you flow visualization, the oil-based Okay, so again, I'll describe the flow as we come to it. This is again the Glaude Goldschmidt body that you have been seeing so far. You have the flow going from the upstream and up top to downstream, and on the right you can see the profile of the body. So if you can look at the right, you'll see suddenly the body starts curving, dipping, where you have the flow separation, and then you have a reattachment subsequently somewhere down the slides, down the line. So this initially we begin the flow conditions without the jet, and the flow will soon begin. That's a coating of oil. So you see that this whole area is fairly separated. You don't see any movement out here, and you see these wakes that are pointing upward, which kind of show that you see this wake pointing downward, this wake pointing upwards, which shows that the flow is reattaching at this point. There is a recirculation bubble that goes up there, and then the flow managed to go downstream. And once you turn the actuator jets on, the reattachment line manages to move upstream. So you'll see the jet actuators being turned on, and the flow dramatically moves, changes. So I can see very interesting vertical structures out here, some crazy stuff going on. And sorry, close too early on me. Right, so that brings me to my conclusion. We have investigated the pneumatic and the on the plasma-based actuators for controlling the flow separation to various extent. We have seen the reduction in size of the separation bubble. We have seen a quicker reattachment. We have seen a delay in the separation point. It's not substantial, but there is a delay in separation point. And so far, just to tie it up with the CSL community to say, the control that we've used out here is open loop. It's based on a design point observation of the structures that are already existing in the flow. So we'll observe at a particular Mach number what vertical structures we have, what Strohal number, what frequency they are operating at. Then we'll decide what frequency we need to operate our actuators at, what velocities and things like that. And eventually you see a change in the flow. What we need to go from, where we need to go from this point, eventually we hope to go from this point is to have some sort of feedback and then close the loop by having a closed loop control on that. Yep, that concludes it, and I'm open for questions. Thanks.
So, sorry, I don't know much about aerodynamics, but so your goal then is to keep the flow on the surface,
Right.
like inside of the turbine?
Inside of?
Inside of the compression area of the jet.
It's not really the compression area itself. So if you go back to the first diffuser slide that you can imagine, that I'd shown. Yeah, so out here maybe this might be a better one. So here you see a separation at this point, a detachment, and then you see this separation bubble. What we want is we want this flow, this red part, to flood this whole area. We want the flow to stay attached all the way as it goes down. Or if you prefer the airfoil, we want the flow not to do this whole jumping off the top thing. We want it to stay attached all the way over here.
So does that increase efficiency?
It increases your lift. It doesn't let you decrease the lift. It doesn't let the wing stall. It increases the total pressure that you recover, the ratio of the pressures at the fan face to your inlet in diffusers. It's, yeah. That's me. Thanks. Go ahead.
And what percentage improvement when you were able to apply the optimal control all the time?
The PDAs that we use, the pneumatic continuously operated on jet devices, we saw about 20% of chord length jump in the reattachment point. So I'll define that. The chord length is the length of the body. So if in this airfoil, the chord length will be defined as the distance from the tip to the root, which is like a benchmarking length that you usually use. In our diffuser application, we have seen that the reattachment line that you saw in the movie, it moves upstream by about 20% of the length of the chord. If you think of it, it's very substantial. In engineering numbers, it's very substantial. We are not yet operating at the optimal point because it all depends upon where you place your actuators. Say along this line, do you place them here, up downstream, further downstream? We haven't optimized that yet. But eventually you hope to optimize both the location and the strength of the jet and the size of the hybrid device, things like that. But 20% is what we have achieved so far. Does that answer the question?
And your free variable is how much strength this jet. If you had active control, you can't really move the wheels around. Your free thing is.
It's the frequency of the pulsing in the pulsed laser, pulsed plasma devices. It could be a pulsed jet that we could introduce. So right now we have a continuously on jet that just keeps blowing. We could introduce some kind of whistle form out there which has a mechanical device that basically creates a sinusoidal jet function, and you could control the frequency of that jet. You could control the strength of the jet if you like the CFM, the cubic feet per meter, the flow rate that the jet comes out. So we do have a few variables with us. We could potentially control the deployment of that actuator of the hybrid microgram device that we saw up there. So there are substantial amount of variables.
Is the compressor and the turbine also needs to be changed after you have applied this control?
No, it wouldn't, because these things will be placed upstream of the turbine at the inlet. So in designing it, you don't have to touch the compressors. And the compressors and everyone else is even more happy if they get a flow that is less distorted and has a good Mach number.
But isn't the angle of attack of the compressor blades aligned to this sort of flow behavior, and then it will have to be redesigned?
This thing doesn't really affect flow vectors in the core direction. The core flow direction still stays the same. So if your plane is moving at a high angle of attack, the blades will still see a different core flow angle of attack. But these guys, they reduce the spurious, the normal vectors, velocity vectors that anyways don't really count in your calculation as such. I mean, they are only a nuisance. They are more of a nuisance than any design points.
Okay, we're running out of time actually.
Cool.
So thanks, Nachiket.
Thanks.